Hello everyone. Today we will continue to look at the content of HCIA-Storage. Previously, we have already talked about the process of data writing in solid-state drives. Next, we will officially look at reading. As for reading, first of all, to read some content inside the solid-state drive, first of all, we still have the diagram from the last class, which consists of a total of 8 blocks. That is, there are 8 channels. Each channel corresponds to 1 block. So what about these 8 channels? They are actually equivalent to 8 that we can simultaneously do what? We can perform a read simultaneously. Actually, we talked about this in the class before last. During writing, what can we actually achieve? We can achieve having 8 simultaneously. That is writing to 8 blocks at the same time. We can simultaneously achieve this kind of writing. So here, firstly, when reading is the same. Since you can write 8 at the same time, reading can also be done in the same way. Of course, first of all, regarding the reading unit here, firstly, if you are, according to what we discussed in the last class, if you have 4 KB of data, or data less than 4 KB. In this case, we generally do what? You would directly use a single channel. Why? Because your data, first of all, everyone should note that if your data is 4 KB or less, it can only possibly be stored on a single block. It cannot be separated, this will not be split. Everyone should pay attention to this. That is, our unit is generally 4 KB to perform the writing, including reading. If you wrote 4 KB into a block, when you read it, you can only read from this single channel. So if your data volume is very small, actually when you read it, the speed is not very fast. The speed is actually not particularly fast, because we only have 1 channel. If you have data that is less than or equal to 4 KB, you actually only have 1 channel to read the data. This is a small disadvantage, but this actually doesn't have much impact. If your data is too small to fill the block, then your overall data volume isn't large either, so the speed won't be much slower. When we talk about slow speed here, what are we actually referring to? Mainly, it's about the number of channels. If you are using more channels, it indicates that your total data is relatively large. For example, let's say like with 32 KB, we have 8 channels, right? If each channel is given 4 KB, then in total, it's 32 KB. Now let's assume we are reading 32 KB. When reading 32 KB, each block will definitely have data in it, right? At this point, when reading, it's equivalent to using 8 channels to read 32 KB simultaneously. So on average, each channel reads at a speed of 4 KB. The time spent on this is actually similar to reading 4 KB. It's about the same. But overall, it seems that reading 4 KB is a bit slow, right? You see, I finished reading 32 KB in 1 second, and you also finished reading 4 KB in 1 second. This actually indicates that, right? The smaller the data volume, the overall reading speed will also decrease somewhat. Of course, this generally speaking, we don't really notice it very clearly because why? Because with such small units, the impact isn't significant. Whether it's a few KB or a few K of data, it doesn't really matter if it's 1 channel or multiple channels, right? It only takes a few milliseconds to download. So, although the transmission efficiency for particularly small files is indeed relatively low, the speed is not slow. Efficiency and speed are 2 different concepts. Here by speed, we mainly refer to time, like your download time, which doesn't really differ much. It's just that for small files, your transmission rate is relatively low, meaning how much you transfer per second will be slightly lower. Actually everyone, for example, you can try it yourself on a USB drive, because a USB drive is actually quite similar to our memory. It's actually quite similar. What can you try on a USB drive? You create a particularly large file, a single file. Then create another one of the same size. A few thousand small files. You can try transferring them. Actually, you will realize an issue. If there are thousands, for example, we use 1 GB in size, 1 GB in size. One is a single compressed package, and the other is 1,000 small files. Which one is faster? Definitely the 1 GB compressed package is faster, because with a 1 GB compressed package, we have a single file that can be read or written continuously through multiple channels. If we have 1,000 small files, for example, 1,000 1 megabyte files, or even more, like 2,000 or 3,000 smaller files, the more files there are, the slower it will be. This is because as the number of files increases, the size of each file becomes smaller. If the files are too small, you won't be able to achieve multi-channel reading, you won't be able to perform multi-channel reading and writing, and in such cases, the overall efficiency will be slightly slower. For the same total size, it will take more time. That's the basic idea. So, when transferring some files, what can you do if you encounter many small files? Well, you can solve this problem by creating a compressed package, combining multiple small files into a single unit. This way, reading and writing become more convenient. The speed will also be faster. This is a basic process of data reading on our solid-state drives, right? Just like the 8 channels in my image. When reading data, it is generally evenly distributed across the blocks of each channel. This way, we can simultaneously read data in parallel from these 8 channels. It's equivalent to having 8 production lines working simultaneously, which is definitely faster than just one production line. This is actually, for example, the read speed of 32 KB can be 8 times that of the 4 KB read speed. This is a major advantage of solid-state drives compared to traditional mechanical drives, as transferring large files is extremely fast. Of course, for small files actually. Of course, there won't be many files as small as 4 KB, there actually aren't that many. For such particularly small files, if the quantity isn't large, it doesn't significantly affect your overall speed. The impact is not substantial. Of course, there's another situation, which is, well, if your storage is not on all the blocks, there will be a certain decrease in speed, which is quite normal. It's not that all the data can be evenly distributed among them. This presents a problem, for example, like what we mentioned earlier. When writing, right? You might encounter some invalid data, right? You might encounter some invalid data or already invalid old data when writing. In this situation, actually before erasing, the places where you can write are actually quite limited. Before a unified erasure, you can write wherever there is space. In this situation, it might lead to uneven distribution. For example, if you distribute 32 2i of data among these 8 parts, it's not necessarily 4 kbars each. One might be 10 kbars and another might be just 1 kbars. This is possible, and it can happen. Some people might encounter uneven distribution, which can indeed have an impact on speed. Of course, this mainly applies to small files, as used in our example. If you're dealing with large files measured in MB or GB, the impact is not particularly significant. However, there is still some impact, as you can never guarantee that all blocks are perfectly evenly distributed regardless of the file size. It's basically impossible to ensure a perfectly even distribution. So this is the main, albeit minor, drawback. But overall, the advantages outweigh the disadvantages. In general, whether it's reading or writing, the speed of solid-state drives is very fast. Indeed, very fast. Of course, other factors that affect reading include the inherent characteristics of the flash memory chips themselves, which can also impact reading speed. For example, after a storage unit has undergone numerous read and write cycles, its performance will gradually decline, which is normal. Additionally, there's the caching mechanism. Solid-state drives also have caches. It's not that solid-state drives don't have caches. Their overall speed is actually also influenced by this. Right, most of them are not as fast as memory, so the cache here is also necessary. Solid-state drives need a cache as well. Although their speed is already much faster than traditional hard drives, they still require a cache area for temporary storage to temporarily store and save some data. This is the overall process of how our solid-state drives read data. The main advantage here is actually parallel reading. The larger the file, the higher the efficiency. So this is the complete data reading process of our solid-state drives. Okay, if anyone wants to learn Washington technology or obtain the Washington question bank, please send me a private message or leave a comment below the video for technical exchange. Alright, that's it for today.